Rabi oscillations and single quantum gates. Rabi oscillations are a fundamental phenomenon of quantum optics, a phenomenon that finds its applications in many practical problems of quantum mechanics. This video presents, in my opinion, one of the most elegant derivations of the Rabi oscillations, and shows how they are related to the execution of single quantum gates. Rabi oscillations are the behavior of a two-level system driven by near-resonant radiation, which leads to the oscillations of the state population. So, if we have a two-level system in the ground state, we can irradiate it with resonant frequency and change its state. For example, bring it to the excited state and back. If we measure a population of the energy levels over the time during which the irradiation is applied, we get oscillations, Rabi oscillations. So, let's move on to a formal study of the subject using the electron as an example. First of all, I think it's important to have some picture in mind of how Rabi oscillations could be observed in an experiment. For example, we have a rubidium vapor cell. In other words, rubidium atoms which are sealed in a chamber. We want to use one of the electrons in an outer shell to study Rabi oscillations. Of course, I simplify a picture a lot. To create a two-level system or a qubit out of an electron, we apply a magnetic field along the z-axis using, for example, Helmholtz coils, and thus cause the Zeeman effect. By doing so, we create two possible energy levels that the electron can occupy. Also, the presence of a magnetic field causes the precession of the electron around the z-axis. If you want to learn more about the dynamics of the two-level system, you can watch my video on the spin-half system in an external magnetic field. To induce Rabi oscillations, in addition to the static external magnetic field, we need to apply an oscillating magnetic field which is orthogonal to the static one. To do that, we use another pair of Helmholtz coils. In the case of solid-state spins, it can also be some kind of microwave antenna in the vicinity of the experimental system with an electron spin. In the simplest case, this can be just a wire. The yellow point shows one of the possible positions where the system can be to fulfill this condition. So, if we pass an alternating current through the wire or the coils, it will generate an oscillating magnetic field. To observe Rabi oscillations, one needs to collect all the electrons at the same energy level, so they all should be in the same state. Apply alternating current of a certain frequency, vary the duration of irradiation, measure the state of the electrons, and see what happens. Okay, thus the total magnetic field B has two components, Bx and Bz. Our task is to calculate the evolution of a two-level system under a Hamiltonian generated by this magnetic field. For this purpose, we construct the Hamiltonian. Recall the formula of the Hamiltonian describing the interaction of the spin with an external magnetic field. We apply it, taking into account that in the considered case we have two vectorial components of the magnetic field along the x and z axis correspondingly. Also, the time-dependent magnetic field will oscillate as cosine omega t plus phi. This is just the most general case. Omega is the frequency of the oscillations, t is time, and phase shift phi is important for our future considerations. The amplitude of the static external magnetic field is sometimes called B0, and the amplitude of the oscillating field is B1. It is important to note that the Hamiltonian is written in units of circular angular frequency, and therefore doesn't contain reduced Planck constant. Then, we introduce two important notations. Omega 0 is a frequency between two energy levels of our two-level system, which is also the transition frequency and the magnitude of the Zeeman splitting. Omega 1 is just gamma B1 and not related to any transition. And finally, we have omega, which is just the frequency of the oscillating magnetic field. It can be larger, smaller, or equal to omega 0. All the frequencies are circular frequencies, so remember about the factor 2 pi if you calculate something. Using these notations, the Hamiltonian can be written in a more compact form shown on a screen. Traditionally, the static part of the Hamiltonian is called h0, and the time-dependent part of the Hamiltonian is usually denoted as h1. To find an expression which defines the state of a two-level system at any moment in time, we need to apply a time evolution operator generated by this Hamiltonian to the initial state. The time evolution operator is shown in the red frame. It cannot be expanded in a familiar way because now the Hamiltonian is time-dependent and the metric exponential contains an integral. So it is a computationally difficult problem. The standard approach to finding the solution is to make a transition into a rotating frame of reference where the Hamiltonian will be time-independent. To make the transition smoother, we need to apply some changes to the lap frame Hamiltonian. We start from the decomposition of h1 into two counter-rotating terms, using the relation shown on the screen. In physics, one can also induce optical Rabi oscillations using lasers. So, this decomposition is equivalent to taking two sources, circularly polarized in different directions, instead of taking one, which is linearly polarized. Then we rewrite the expressions in the red frames. Let me introduce you the sigma plus and sigma minus operators. Sigma plus acts on ket 0 to turn it into ket 1. Sigma minus does the opposite. These operators do not represent observable quantities because they are not Hermitian and do not have any association with a physical process. If you remember the creation and annihilation operators for the quantum harmonic oscillator, the raising and lowering operators for angular momentum, the sigma plus and minus matrices are just the spin-half versions of these operators. For us, these are just convenient mathematical operators. We want to write down cosine omega t plus phi sigma x plus sine omega t plus phi sigma y in terms of sigma plus and sigma minus. First, we use the expressions for sigma x and sigma y, then we multiply two matrices according to the matrix multiplication rule, and after that, we get the desired expression. We can repeat all these calculations for another expression in the red box. Finally, we substitute them into the original formula and obtain the expression for the Hamiltonian in the lap frame, which we are going to use in our further calculations. Now it is convenient to go into the frame, rotating along the z-axis with frequency omega, which is nothing else but the frequency of the applied oscillating magnetic field. The corresponding transformation is described via the following unitary operator. The Hamiltonian, which generates this evolution, is omega sz, has the units of frequency. We can introduce a parameter theta, which is equal to omega t, and decompose the evolution operator to cosine theta half I minus I sine theta half sigma z. The state vector in the rotating frame can be obtained by applying the evolution operator to the state vector in the lap frame. The Hamiltonian in the rotating frame of reference can be found using the following equation. The derivation of this formula is shown in my video about the Hamiltonian in a moving frame of reference. In the red frame, you may see the same equation, but written in a more compact form. So, let's perform a transition to a rotating frame of reference and calculate the first term. We use the expression for the Hermitian adjoint of the evolution operator and the fact that it is unitary. Then we just perform calculations, taking the derivative of a complex function. So the first term is just minus omega divided by 2 multiplied by sigma z. Now we move to the second term. Using the expression for the Hamiltonian in the lab frame, we get sigma plus and sigma minus operators sandwiched between the evolution operators. The calculation of the corresponding sandwich formulas will be shown on the next two slides. I will not comment on them. If you have something unclear, please watch the video about the sandwich formulas for rotation operators. Here is the derivation of the sandwich formula for sigma plus. And the same one can do for sigma minus. We get two short and elegant expressions. In the next step, we just use them. And then we just simplify the expression. As you may see, inside the first brackets, we have exponents containing 2 omega. And that is the only time-dependent part of the Hamiltonian. At this point, it is customary to make the so-called rotating wave approximation. Under the assumption that omega 1 is much less than omega, we can discard these fast oscillating terms, because they are small and quickly average out during the evolution of the system. These were some standard phrases from the textbooks, so let me clarify what is happening. We are calculating the Hamiltonian in the rotating frame because afterwards we want to get an evolution operator and apply it to an initial state of a system. So far, the Hamiltonian is time-dependent. Therefore, we have an integral over time in the evolution operator. The only time-dependent part of the Hamiltonian in the rotating frame is an oscillating term in the red box. What happens if we take an integral over an oscillating function? The result will be either positive or negative or zero. It will also oscillate. If this oscillating contribution will be small enough, we can just neglect it. The other part of Hamiltonian is minus omega divided by 2 sigma z. Now you can see the full picture. To have a small contribution to the integral from the term in the red frame, omega 1, which is the amplitude of the oscillations, must be much less than omega. So, we applied the rotating wave approximation. If we make a little analysis of what has happened, we can notice that basically we removed the term which rotates clockwise, because it's originated from cosine plus sine. This means that if the oscillating magnetic field is circularly polarized anticlockwise, we do not need to do any assumptions and apply RVA. Finally, we combine two parts and introduce a new parameter, delta omega. Delta omega is the difference between omega, the rotation frame frequency, in other words, the frequency of the applied magnetic field, and omega 0, which is the transition frequency of the two-level system and the Larmor frequency. We will see an interesting effect when the speed of the rotating frame will coincide with the frequency of the Larmor precession. Now let's have a closer look at what we got. In the rotating frame, we have a Hamiltonian, which is time independent. Also, it is a linear combination of all three Pauli operators. We rewrite it in the following way. Now we want to normalize coefficients in front of each Pauli operator. For this reason, we introduce another parameter, big omega, which is a squared root from all numerical coefficients squared. We put the big omega out of the bracket. Now we can define a unit vector n, and voila, look what we got. That is a Hamiltonian which generates a rotation operator. Here we go. Just as a reminder, the rotation operator can rotate a Bloch vector in any other Bloch vector, which includes all possible qubit states up to a global phase factor. Here, vector n is a unit vector which defines a rotation axis, and alpha is a rotation angle. So, if we are looking from the rotating frame, the action of the one static and one oscillating magnetic field creates a Hamiltonian which generates an operator which allows to perform arbitrary rotations on the Bloch sphere, of course as far as the parameterization allows. Our vector n is not arbitrary, it is parameterized. Our final goal is to find the state of the system at any moment in time. In the general form, we want to find the coefficients C1 and C2. If we are talking about an ensemble of spins, it is customary to speak of state populations. The standard way to find C1 and C2 is to solve the Schrödinger equation. If we use the matrix representation of the Hamiltonian and represent psi as a vector, the Schrödinger equation gives rise to a system of two linear differential equations. This system looks simple, but it is quite unpleasant to solve it analytically. We will work with an evolution operator instead. So, we are interested in how the system will behave under the action of the evolution operator generated by the rotating frame Hamiltonian. We take state 0 as an initial state because this state is the same for both frames. I hope that it's obvious. And now, apply the time evolution operators to this initial state using the decomposition of the matrix exponential for self-inverse operators. And write down n sigma product via sigma plus and sigma minus. Here we use the relations we got earlier in this video. Next, all the operators act on a ket 0, and then we group the terms around ket 0 and ket 1. And we got it. The expression that describes the state of the system at any moment in time in the rotating frame. By the way, now it's also possible to get an expression for the state vector in the lab frame in a general form. On the one hand, we have an equation to go from the lab frame to the rotating frame. On the other, the equation for the evolution in the rotating frame, we just used it. Combining these two equations, we get an expression for the state of the system in the lab frame. At last, we have everything to calculate what we will see in an experiment. According to the measurement postulate, the probability to measure the qubit in state 1 is the following squared inner product. We expand this expression according to the rule shown on the screen. After some simple math, we get the formula for the probability to measure state 1. The probability to measure state 0 can also be obtained from the measurement postulate, and it is 1 minus probability to measure state 1. Let's analyze what we just got. Consider the general non-resonant case. On the left side, you see the probability to measure state 0 as a function of time. And on the right side, the probability to measure state 1 for different values of delta omega. Delta omega is equal to 0, 0.5 omega 1, and omega 1. Delta omega is the difference between the transition frequency and the frequency of the irradiating field. The probabilities to find the system in state 0 and 1 oscillate with frequency big omega. These oscillations are called Rabi oscillations. And the big omega is called Rabi frequency. Big omega determines not only the frequency but also the amplitude of oscillations. In the non-resonance case, when delta omega is not equal to 0, the amplitudes never go from 0 to 1. It means that in the off-resonance case, there is never a unit probability that the spin goes from spin up to spin down. Therefore, the resonance case is of particular interest. At resonance, the frequency of the applied magnetic field coincides with the transition frequency. It also means that the frequency of the rotating frame coincides with the frequency of the Larmor precession. Only at resonance the state goes from ket 0 to ket 1, and the amplitude of Rabi oscillations is maximal. If we now calculate the expectation value of the SZ operator using the formula shown on the screen, it will be just cosine big omega t. The spin goes up and down following the cosine law. At resonance, the Rabi frequency depends only on the omega 1, in other words, on the amplitude of the oscillating magnetic field. Let's look again at the graphs of how the probabilities and the value of SZ expectation value change from the time for which a variable magnetic field is applied. The graphs show what we see in the lab frame, of course. The question is, what happens with the other spin components, Sx and Sy? So, let's look at Rabi oscillations on the Bloch sphere. We are still at resonance, and I have chosen the Bx field which oscillates as sine, so that phase phi is 0. Below you may see the corresponding Hamiltonians in the lab frame and the rotating frame. The lab frame is processing with Larmor frequency. The Bloch vector outlines a spiral which goes from spin up state and back. And what happens in the rotating frame? Yes, the rotation around the x-axis of the Bloch sphere happens. That is not surprising at all, because the Hamiltonian in the rotating frame is just the Pauli X operator with a numerical factor. You can probably see where I am going with this by now. Microwave irradiation of a two-level system gives rise to a basic quantum gates. As I already showed you, the action of the one static and one oscillating magnetic field creates a Hamiltonian, which generates an operator which allows performing arbitrary rotations on the Bloch sphere. However, vector n, which defines the rotation axis, is not arbitrary. It is parametrized. Let me tell you a secret. I intentionally took by x with an undefined phase so that the phase would then be present in the Hamiltonian in the rotating frame of reference. The Hamiltonian consists of sigma x and sigma y, which means that it generates rotation around x and y axis. Indeed, if we calculate vector n, it depends only on phi, in other words, the phase of the applied field, and lies in the transversal plane of the Bloch sphere. The pink arrow indicates vector n, and the orange arrow indicates a Bloch vector which rotates around this vector. The rotation angle of the Bloch vector is equal to the big omega t. If we apply an oscillating field during a certain time, so that big omega t is equal to pi, the spin goes from spin up state to spin down. This is the so-called pi pulse. If we apply a pi pulse with chosen phase, we perform a quantum gate. When the phase of the applied field is equal to 0, we perform the x gate. For the phase minus pi half, we perform the y gate. Now let's see what it looks like in practice. We have a spin or an ensemble of spins in a static external magnetic field, so that you already know the splitting between the energy levels, omega 0. And we need to set parameters for the oscillating magnetic field. So, what we have? The amplitude of the oscillating magnetic field, B1, defines the Rabi frequency and, as a result, the duration of the quantum gates. Here we should take rotating wave approximation into account. When RVA is not applicable, it is a strong field regime, and this topic is beyond the scope of this video. The frequency of the applied field should be resonant. Omega should be equal to omega 0. If you want to perform a quantum gate, for example x or y, you choose the phase because it defines the rotation axis, and fixed time so that big omega t is equal to pi. In the end, I would like to show you what happens with Rabi oscillations when we begin to violate the condition set by rotating wave approximation. These are exact simulations made with QTIP, a quantum toolbox in Python. In the graph, you see the SZ expectation value as a function of time. We begin with the case when omega 1 is 100 times smaller than omega. We see an ideal cosine. Then we start to increase omega 1. We increase it by a factor of 10. In the blue graph, we begin to see the tremor superimposed on the cosine. Increase the amplitude of the alternating magnetic field 5 times more, the green curve. Now we see distinct wiggles caused by the deviation from rotating wave approximation. Do you remember we discarded the rapidly oscillating terms whose contribution to the integral can be both positive and negative? So, they are the ones that cause such small wiggles. At omega 1 equal to omega, it is already hard to recognize cosine. You can try everything I tell you here if you are a physics student and are doing lab work on the optical pumping of rubidium atoms, for example. As a conclusion, I just want to repeat that resonant derivation of a two-level system induces Rabi oscillations and gives rise to basic quantum gates.